So, welcome everyone for this webinar at eSpace. So at eSpace, at EPFL Space Center, we like to do webinars on a frequent basis. And now we're very happy to have Justin Bourgois with us. He's going to talk about his experience at the Concurrent Design facility. So what is Concurrent Design and Concurrent Engineering, his experience at the CDF, and also maybe interesting for the students following now, how you can enter ESA as well through the, for example, Young Graduate Trainee program. And I think Justin has a lot of interesting things to discuss. So for your information, the meeting is recorded. So if you have any issue with that, you can let us know in the chat. But otherwise, we plan to put it on YouTube as well. So Justin is, well, someone who graduated from the Delft University of Technology in Aerospace Engineering. And now he's, if I'm not wrong, you'll correct me, already 2 years working as a system engineer at the ESA Concurrent Design facility. And he has contributed to many of the early design projects that ESA is doing at the moment, but I believe Justin will be elaborating on this a bit more. So Justin, I'll let you speak now, and then afterwards we can have a Q&A session for those who have questions. So do keep in mind, if you have questions, you can write them in the chat, or we can discuss them through a camera or just with a microphone. So Justin, you can go ahead.
Yeah, thank you, Marnix. Good afternoon, everyone, and welcome to this presentation on concurrent engineering and the concurrent design facility at ESA. Marnix has already started to introduce me, so I will not be too long with my introduction, but yeah, I'm an aerospace engineer from Luxembourg. I studied in the Netherlands at TU Delft. I've done my master's and bachelor's degrees there in aerospace engineering, and then I specialized into systems engineering and propulsion for space flight. And then right after my studies, I joined ESA at their center ESTEC in the Netherlands for 2 years of traineeship, working as a systems engineer at the Concurrent Design Facility, the CDF. And there, as part of my work, I've participated in over 10 engineering studies for potential future missions, so anything ranging from CubeSat missions to science missions and Mars exploration. So yeah, today in my presentation, I will mostly focus on what the Concurrent Design Facility is, how it works, how it is being used, some of the benefits of working that way. And then I also have a few slides on my work and my experience as a trainee at the CDF and at ESA. And I'll conclude with slides on opportunities at ESA for students and people who recently graduated. So let's get right into it. So what is the CDF? So the name is Concurrent Design Facility. So with facility, you might think it must be a building, a room, or a lab, or something like that. And indeed, there's some of that. But to do design studies, you need more than a facility. So is it also a team, a set of IT tools, is it a methodology? I'll try to answer those questions, and then we'll get back to this one later on. But let's start with what is the CDF mostly used for? So the primary use of the CDF in general is feasibility studies and early phase design. So on this slide on the right, you can see I have a table with the typical design phases for space missions. It's generally started phase A, or sometimes also phase 0 already, and then goes through all the phases until phase F. So phase 0 is mostly identification of the mission objectives and requirements. Then in phase A, it's feasibility studies, phase preliminary design, and goes to detailed design, qualification and production, launch and utilization, and then finally disposal in phase F. As part of the CDF, since we mostly do feasibility studies, you might think we work mostly in phase A and perhaps in phase B for preliminary design, but actually most of our work is really focused on phase 0, and some of it also a bit on phase A. Hopefully in a few minutes you'll understand why. So when we do a feasibility study at the CDF, generally the way it works is we have a customer. Most of the time that's internal to ESA. It can be an ESA directorate or department that comes to the CDF team and tells us we have an idea for mission, or we've received a proposal from research institutes or universities to go study something somewhere in the universe. We would like to make a mission out of that. Can you study if this is feasible? And they then also provide us a first set of mission objectives and mission requirements. And those are really the inputs for a feasibility study. Then the process of conducting a feasibility study itself is mostly centered around making a preliminary design. So based on the inputs we receive, we try to design something that fulfills those requirements. And during the design process or after first iteration of the design, quite often we then have to go back to the objectives and requirements and check which ones we have already fulfilled, which one we think we can achieve, and where there are issues. Because some of the objectives are performance objectives, performance requirements, but then there's also many constraints that come as an input. For example, a budget limits or a date by which we want to launch a mission, or just the availability of technologies. And so from the first preliminary design, we can reassess the objectives. And quite often there's a need to then adjust them, maybe rescope the science requirements, or accept that the fact that the budget will be higher than initially expected, things like that. And then the inputs gets adjusted, and the design can be iterated on again with those new inputs. And so with this design cycle, we can generate a few key outputs, which are, of course, the main one, the feasibility assessment. So is the mission feasible? Yes, no. But often it's not quite that clear cut. It's more of a yes, but we have to adjust these things from the initial objectives, or yes, but we will need a higher budget, and those kinds of things. Along with that, of course, we get a preliminary design. And another really important output is a set of consolidated objectives and requirements. Because during the process, we use those requirements and objectives as inputs, but we also refine them. If we see that some of them can be adjusted just a little bit and it will make the mission so much easier, then this is really valuable input for future design work. And along with that, we also add some new requirements that were maybe not included from the start, but that become relevant during the design process. So with all of this, the CDF is really a very useful tool for decision making, because not only do you get to find out whether your mission is feasible, but you also know a bit more detail about it already. You have a better estimate for the budgets, for the technology developments that need to be done to be able to launch the mission on time, and all those types of things. So the results then get used by the customer who requested the study to get approval for the mission if they decide to proceed with it and go to the next phases. And they can use the CDF study reports as a justification to get funding from the ESA member states and proceed with the mission. So this is roughly how feasibility studies work in the context of the CDF and what they are used for. Then we can go to how this works in terms of study team and the timeline of a study. So generally for a CDF study, we have a core team made out of the systems engineers, about 3 or 4 systems engineers, along with the customer who requested the study. We try to involve the customer as much as possible, because that makes the process a lot smoother. It's easier if we can have direct feedback during the design process from the customer and make decisions while involving the customer. And then additionally to that, we also have 20 to 30 domain experts that come from different disciplines. So quite often we have 10 to 15 disciplines. Those might be things like mission analysis to design our trajectories, propulsion experts, structures experts, from all the subsystems you could imagine on a satellite or a space missions. Those are generally involved, but then you also have other domains like a cost expert to get a feeling for the budget that will be needed for the mission, a risk expert or programmatics expert as well. So there's quite a large team of people working on these studies and from all kinds of disciplines. And we try to tailor the disciplines we have for study and depending on the needs of that study. And so it's not always the same types of experts, but it depends on the mission and on the study objectives. In terms of timeline, CDF studies generally last 1 to 1.5 months. So we have 7 4-hour sessions starting from the kickoff and then design sessions, and we do 1 or 2 per week. And in between sessions, of course, the experts also work on the design process, but the sessions are really the part where all the inputs come together and where the collaborative part of the design happens. And then we conclude the studies with a full day session where all the inputs, all the design work is presented and reviewed. This then flows into a report that is the main study output. And during that time, we can do 2 to 3 iterations typically, and also assess different design options and perform many trade-offs on the mission design. So far this has all been quite standard and general for any feasibility studies or design projects in early phases. So what makes the CDF and the concurrent engineering approach special? Well, it's really the approach to how we collaborate. So the more standard approach for design work is to have a more sequential approach to design. You start with the inputs and then one domain, typically that would be mission analysis is a good place to start because their inputs will drive a lot of the rest of the design. They will have to do their design work, do a first iteration of that. But since they are working on their own, they have to make many assumptions. They are not always the right person to make these assumptions. They don't have all the expertise in other domains. So they do their best, try to make assumptions, make their design, and then hand over the design to the next step in the chain of design. And that next engineer then designs their subsystem and uses the inputs from the previous step to do that. But this process is quite slow since everyone has to wait on the previous team to do their design. There's clear challenges with making assumptions. Not everyone will make the same assumptions. People making early assumptions will maybe make assumptions that are not relevant later on in the design. And the design consistency is not always great with this approach. One way to improve that is to use a more centralized design approach. So there, the idea is to introduce a systems engineering team at the center of the design team that acts as the coordinators of the design effort and as the interface between the different domains and disciplines. But this is also not ideal because even though the different domains can now work simultaneously, having all of the information interfacing through the systems team can create a bit of a strain and a bottleneck on the design process. So this is why we use the concurrent design approach, where we try to have everyone interfacing with everyone and working in parallel. So rather than having a systems engineer doing the data and the information exchange between the team, everyone can directly exchange the data with the other subsystems and you only have a systems team to coordinate the design and drive the design in the correct direction overall, but not anymore as the link between the disciplines. So here the tricky part is to achieve this data exchange in real time and to allow the different domains to work concurrently. For that, we use mostly a central data model. So this is where the design happens. In every discipline works on their subsystem design, but then they all provide the key parameters of their design, the outputs of their design into one central model that everyone has access to. And so everyone can also retrieve information from that data model. And this is then where the design of, for example, satellites takes shape, input by input. At first, it's really rough estimates. That's one domain puts as first guesses, but then someone else uses these inputs to refine their design. And that way, with a constant data exchange, everyone has the latest values and can coordinate the design without making assumptions that are very widely off or having an inconsistent design. Yeah, this slide looks a bit messy, and that's somewhat intentional. It's because the design process that you have to go through to design a space mission, but also many other things, where you have many disciplines, many subsystems, can be quite complex. So if we start on the left-hand side, we have the mission requirements and constraints. Those are the inputs we get at the start of the study, as well as just underneath, we have the study requirements. So this is what the study specifically should achieve, because you can have different objectives. It's not always an overall mission design, but it can be focused on a specific aspect. And then all of this feeds into the complicated interweb of the different disciplines. So if we take the typical starting points, like mission analysis or instruments, from mission analysis, once that design is done, you can do the thermal control design and the propulsion design, which then feed into the structure, which all of these then also feed into the dry mass of the spacecraft. And similar from the instruments themselves feed into the dry mass of the spacecraft, but also have an impact on data handling, communications, and the electrical subsystem. And all of this then results in dry mass estimates, wet mass estimates, and so on. But since everything is so interlinked, and in reality, I'm sure you could even add more arrows than we already have here. This is one of the key reasons why it's challenging to do a good sequential design, because it's not that you can start from one place and then just neatly go from step by step to the next domain or next subsystem and then end up with your final result. But this is really why it's key to have everyone working together simultaneously and exchanging data all the time. And then from this, you get the study results. Plus, of course, there's also the arrow feeding back into the mission requirements and constraints, as those are part of the things that get refined through the engineering process. Yeah, and then on this slide, this is to illustrate the iterative nature of the design process. So also with a sequential design, you would have to perform iterations, and probably even more so than with the concurrent approach. But still with the concurrent approach, you do still need iterations because you start from requirements, and then from mission analysis, you can start doing your subsystem design, verify it, do a risk assessment, a cost analysis, but then that feeds back into the mission requirements, and you can repeat the cycle. And hopefully, as you keep iterating, your unknowns get smaller and smaller. You refine your design, it gets more and more consistent. Your requirements get more and more specific, and you converge to a design that is quite refined where there's not too much uncertainty in the design of each subsystem. And yeah, that's how you end up with a viable preliminary design. So yeah, I hope I've more or less given you an idea of what the CDF is. So team, room, IT tools, methodology. Well, it's clearly a bit all of it. So we need the team of engineers, the systems team, the customer, the experts. We need a room to host all of these people. So you can see here on the picture a nice model of the room we work in. This is a Lego model done by one of our colleagues. And this room is also part of the infrastructure we really need, because everyone needs to be able to work simultaneously on their tool, on their design. So each desk has a workstation. We have large screens to present the design of the different subsystems. We also have screens to keep an eye on the systems budgets, so mass budgets, power budgets, and so on throughout the study. And we also have video conferencing equipment. Even though we like to have the people in the room as much as possible, we always end up having some people online, especially from mission analysis and the ground segment. Those teams tend to be based in ESOC in Germany rather than at the ESTEC facility in the Netherlands, so they always join us online. And then yeah, the IT tools, one of the key IT tools is our central model to exchange the data. At ESA, we use a software called Comet, but you could use other tools as well. It could be as simple as just Excel workbooks or something like that. And then each of the subsystems also uses specific tools, be that simulation software, CAD software, or yeah, also Excel workbooks. And then there's the methodology, the concurrent approach, which is key to making the whole thing work. So some benefits of the concurrent engineering approach and the CDF is that since everyone is in the loop for everything, we can do faster design cycles and converge more quickly to a consistent design compared to more traditional approaches to design. The fact that we also have experts that do studies on a regular basis really helps with having experience in the team. People who take part in CDF studies, apart from the systems team, they generally don't do that as their main job, but they still do at least a couple of studies per year. So we really have experience building up on just their specific work for their subsystems in preliminary or early phase design, but also the whole concurrent approach. And then we have a rather standardized workflow and design process, and the outputs as well tend to follow a certain format. So that way we are able to guarantee a high quality of outputs, of results, and the whole thing at a rather fast pace and reduced costs to other approaches. So the CDF has been going on for over 25 years now at ESA. And many of the missions you might have heard about from ESA, not all of them, but many of them went through the CDF at some point or were even born in the CDF. So I've included just a few examples here that are more recent on this slide, just to give you an idea of which missions came through the CDF. So we have the ExoMars missions, which have faced some delays, but should hopefully launch in a few years to go explore Mars with a European rover. And then there's JUICE, that's the Jupiter Icy Moons Explorer, which is on its way to Jupiter. And I've also included Euclid and Cheops, two space telescopes. The reason I've included those here is that, as far as I know, both of those have involvement from Switzerland in the missions, especially Euclid, I think, is in partnership with EPFL, or was at least. So yeah, many of the projects that you hear about these days went through the CDF at some point. I've mostly covered the part of early phase design and feasibility studies so far, but in general, you can apply the CDF and concurrent approach to many other things. Pretty much anything that is problem solving with a really multidisciplinary team could be done in a similar concurrent approach. And that's why at ESA we also have other activities, so not just feasibility studies, but also technology road mapping, education and training activities. So we regularly organize small CDF studies with students at a CDF facility in Belgium at the ESA Education Center. We also sometimes do reviews concurrently and support industrial activities and do validation of industrial activities. So these are just some of the options that can be done with the concurrent approach. So that was the first part on the CDF and concurrent engineering. Now I will cover a bit what I did as a trainee at the CDF, how I was involved in all of this. So in my 2 years there, I've done around 11 studies from different directorates, so mostly from science and exploration, but also a couple from operations and one from space transportation directorate. And most of them were around Earth, but I also had 3 missions that I planned to go to Mars. And one that was a bit less well defined, so there's more than just Mars and Earth as options. As a trainee, what do I do during a study? So at first, when you start as a trainee, it's a bit of secretary work mostly, so managing invitation, managing the infrastructure of the room, but also one of the key points is to run the central model, so making sure it works, setting up the structure for the design architecture for the system, how we want to break it down, do we have multiple spacecrafts in the mission, and so on. And then making sure we get all of the inputs from the different disciplines, making sure the inputs are valid, helping out the experts with interacting with the model, and then generating the outputs from our central model that the experts can use. So that's mostly mass budgets, power budgets, equipment lists, these types of things. So this is really the basics. When you start out, you mostly do that, but after a few months, when you start gaining experience, that's where the real fun starts, because at that point you can also really be involved in the systems engineering work and contribute to the design process. So this is for me the part that I enjoyed the most, just being part of the discussions, having my say in trade-offs, and being able to question requirements coming from a customer. One nice example I had is during one of the studies for a more scientific mission where we wanted to study gamma ray bursts, and the customer had specified that we should have 100% availability for the constellation of satellites we had. However, as you can imagine, 100% availability can be quite challenging to achieve and will really drive the design. So just by questioning why we needed that 100% availability, I managed to get that requirement changed to a much lower availability. And to make up for that, we just extended the mission duration by a few months. So we had the exact same science output, but it made the whole design process a lot easier because you can have lower reliability, longer periods where you perform other tasks, maintenance, and so on. And so it's just, through asking these small things to customers or to experts, making sure they have already thought of ways to make things simpler, and then, if not, implementing these simplifications. That's where it's really interesting to be part of the process. Of course, I did not just do CDF studies, since there's always some time between the sessions or between studies to do some other work. So my primary focus in terms of side projects was improving the concurrent engineering process and the tools we use. So I've already mentioned Comet, the software you use as a central model for the studies. It's a reasonable tool. It works well for what it's supposed to do, but it has some shortcomings, especially in terms of user friendliness and getting outputs from the model. So one of the key outputs we always get is mass budgets and power budgets. And since we are working in a very collaborative way and doing really real-time design, it's nice to be able to present a budget and discuss it. And if there are any changes, make them right then and there. And with the standard Comet software, this is not possible because all you get in terms of budget is just a table that is static. You cannot change anything, or if you make changes, they will not be fed back into the model. So I spent quite a bit of time developing my own little software, which interfaces with the Comet models and is able to generate budgets, but budgets that are interactive. So you can change the values in the tables just in the same way as if you were working in Excel, and then the changes you make will be fed right back into the model. So you have truly interactive budgets that can be presented live and then worked on in session with everyone involved. Then other small things I was involved in. So as I already said, there are regular CDF workshops organized with ESA Academy. So as a trainee, I had the opportunity in joining a couple of them and doing the same work I would do in a regular CDF study. Plus, on top of that, also just teaching and coaching students on the concurrent approach and teaching them how to do the design of their subsystems, these kind of things. And then I've also done a few reviews of industrial projects, and towards the end, I've been more and more involved on the Mars side of things. So I joined the Mars X team that does future Mars studies. So it's at a similar phase, so mostly phase 0, phase A for the upcoming Mars missions that ESA is working on. Generally, I really like my experience at the CDF because it's really a great learning experience and a great follow-on to aerospace engineering studies. During my studies, there were certain topics where I thought, okay, this is great, this is interesting, but if I specialize in something, I will never use these things again. But then at the CDF, I pretty much used all of my knowledge from the studies. All of the topics were covered because we work with so many different subsystems, so many different domains of expertise. And the range of missions we do is also really wide. So yeah, it's really small spacecraft, CubeSats in LEO, so in principle simpler things, but even there you can do ambitious missions. And then also, yeah, larger science missions, Mars orbiters, Mars landers, a bit of everything. So that's really one of the nice aspects of the CDF is that you get a very wide experience, and it can really prepare you for later work in any of these domains and help you explore what you really like, what you're really interested in. So yeah, that's it's on my side, on my work at the CDF, my experience. Since I expect there to be a few students online listening and being interested in this, I also have a slide on opportunities to join ESA, to work with ESA. So ESA has a few entry-level programs to get students and young graduates involved in ESA. There's of course internships that you can do as part of your studies. If you have already graduated, but only recently, or you are about to graduate, there's the ESA Graduate Trainees program, formerly known as the Young Graduate Trainees program. So maybe you've heard about YGTs, so this is the same thing. And also national trainee programs in certain countries. I think currently it's still Luxembourg, Belgium, Poland, Lithuania, and Estonia doing this. but I know that Switzerland used to do also national trainee programs. If you are working on a PhD and are about to complete that or already have a PhD, maybe a research fellow position could be interesting. Or if you have 2 to 3 years of experience, there are young professional positions that will open soon. So yeah, those are the programs to really work at ESA. And then there's ESA Academy if you want to do a smaller project or training or workshop with ESA. So in terms of projects, there's, for example, Fly Your Satellites or the Rexus Plexus projects where you can get the opportunity to fly a payload either on a sounding rocket or a high altitude balloon. Yeah, there's many workshops. I'm mostly familiar with the few concurrent engineering workshops we do every year, but there's also other ones on Earth observation, navigation, and many other things. So if you are interested in that, I really recommend you go and check out what's currently on offer on the ESA Academy website. So yeah, that's it for my presentation. I hope you learned something, and I think we can now go to the question round. I know that some of you just conducted or went through a course on concurrent engineering and did a small CDF. So if you have any specific questions on how we do things at ESA or how you could do things on your side, feel free to ask those as well. And yeah, I think all
Yep.
good. Yeah.
Thanks a lot, Justin. So yeah, I think it gave a very good overview of the CDF. And I was also going to say that it matches quite well with what we do at the EPFL Space Center, namely the CDF class we teach, where it's a small team, smaller than what you guys have. For us, it's 10 to 15 people. But indeed, some of the students from the CDF class are here with us and online as well. So if you do have a question, I also have some small questions, but I'll give priority to other people. If you do have a question, you can write it in the chat and or raise your hand virtually or in person here. I can definitely begin with one question that Candice asked, and I think it's a nice one to begin with, is what was your favorite mission among those that you worked on and why?
Ooh, yeah, tricky question. Yeah, I think I have to also make the difference between mission and studies, because yeah, in terms of missions, I really liked. I'm really interested in exploration missions and Mars exploration. So I think for me, the highlight would be designing a Mars lander. But then there are also studies where just the team was really nice or where I got to be a bit more involved. So there I would say it's probably a couple of one study where we did 2 missions with universities for CubeSat missions. And that's one I really enjoyed, just to the way I was involved in that study. And also because one of the 2 teams was a team from TU Delft who had proposed a mission idea, and we were then reviewing their proposal and iterating on their design. So being able to review the design of professors I had met a few years earlier, that was a fun experience.
Mm-hmm. Yeah, I can imagine. I see that also for the people in the room, if you have any question, you can ask them. I see first that Thomas has a hand raised, so you can begin with your question.
Yeah, thanks. Thanks a lot for the presentation, super interesting. I was actually at ESA 2-3 years ago. I was also working on JUICE, and I also took part in a small workshop with the CDF. So I think we briefly met there, but it was interesting. I just had a very brief question on something that you touched on at the very beginning of your presentation, which was that at ESA, at the CDF, you mostly focus on phase 0 and occasionally phase A, but mostly phase 0. So my question is, when a mission is accepted and will be built, are you also following the phases B, C, and D with, let's say, the companies which are building the mission, or not at all?
Yeah, thanks for the question. And yeah, I think indeed we met briefly at ESA. Yeah, so speaking purely about the CDF, we don't really get involved with things at later phases. So what sometimes happens is that we do a bit of shadow engineering for specific aspects of the mission. If we identify, or if the project team identifies there's a particular challenge that needs a bit more involvement from ESA, then we could do a CDF study on that. But for the most part, the work in later phases is done by industry. And then there are project teams on ESA side following the work of industry and doing the reviews there. But since the design is not done by ESA at that stage, we don't do any design at the CDF. And generally, it's also different teams involved in those later phases. So the teams involved in the later project phases would be primarily the customer, who keep on, of course, following their mission. And then they assemble a team of experts that can follow the mission more long term. Sometimes there are some of the experts from the CDF who then keep on following the mission also post-CDF and into the later phases, but it's not done at CDF level.
Okay. And even during the qualification and production, during the test, if they come here if they come to ESTEC for the testing, are you involved a little bit or not at all?
Yeah, on CDF sides, not at all.
Okay.
And that's more on the project teams that are involved in the later phases.
Okay, thanks.
Maybe a small question to clarify also about the importance of the CDF and whether or not you're involved with future phases of the design. What's the timeline from the time that you do the CDF to the actual launch? Also, by the way, thank you for putting those missions involving also EPFL. I think that was a nice touch. But so what is roughly the timeline for those from the CDF to the launch?
Yeah, very good question indeed, because it really depends. So the studies I've done on CubeSats, those are planned to launch in 2027, 2028. So this can take 3-4 years. So that's quite fast from phase 0, phase A to actual launch. But then some of the more complex and larger missions can take quite a long time. The missions I've worked on, so I've included here 2 science missions that were studied in 2023. And those, I think, are planned to be launched at the earliest in 2035 or 2037. So it's 10 years and more, and this is not accounting for additional delays because there have been changes in the program, or there's a collaboration with other countries that didn't go as expected. So yeah, can go from anything to 3 years to 15 years, or in the worst case more, but we hope that doesn't happen too much.
Yeah, thank you. Does anyone in the room have a question?
Yes, when you were answering the question from Thomas before, you said a lot of the design phase, the later phases are done by the industry. I'm just curious about how much of the work is relayed to industry and how much is done inside ESA's facilities. How much is ESA dependent, I will say, in the other industries, in the sense also that I imagine one mission from another, a lot of things would change. So yeah, like how feasible also would it be like to try and do everything at ESA? Yeah, it's multiple questions. I'm sorry.
Yeah. So the thing that's quite important to understand is that ESA is not really an agency that's doing design for the mission. The main purpose of ESA is to really help the aerospace industry in Europe and fund them through by collecting the funding from ESA member states and then using that to really drive and develop the European space industry. So that's why the main purpose of ESA is to identify the missions that are valuable and then use those to redistribute the money that's coming from the member states. And that's also why ESA doesn't do the design and the production of the missions itself. So the way it works typically is that the initial mission idea comes either from research institutes or universities or from ESA itself, or can be requested for other missions, perhaps from the European Union or things like that. And then ESA defines the mission objectives and so on, and provides those to industry, but the entire design phase and production will be done primarily by industry. ESA is there to support them. There are teams reviewing them, advising them. There's testing facilities at the different ESA centers, mostly at ESTEC, so the industry can use those, but ESA does not build the satellites.
Oh, I see. Okay. Could I do a follow-up question to what you said?
Yeah, sure.
So, for example, who decided, gave the idea for the JUICE mission, let's say, and also who decides which industries are gonna be building the mission?
Yeah, so for JUICE specifically, I don't know where exactly came from because it's been studied many years ago, so I wasn't involved in any of that. But for the two missions I have here, Plasma Observatory and Matisse, those are also science missions. And for those, there was a call from ESA for proposals for science missions. And then universities and research institutes looked at what they could do to propose something that fits with the idea of the proposal. Generally, there are some very broad topics that ESA includes in those proposals, that they want to study exoplanets or things like that. And then the different entities make proposals that are linked to that. And that's where the specific idea for the missions come from. And then it goes to ESA to see if it's feasible, if there's interest and value in doing it, and whether it should proceed to the next phases. For your other question on who or how is it decided which industries get to design and build the missions, generally there's a competition process where ESA puts out an invitation to tender or something like that, where they outline requirements and what industry needs to do to design, for example, and complete this design process of phase A for a given mission. And then industry can bid for that, and the best bids then gets to carry out the contracts. That's broadly how it works. I haven't been involved in much of the later phase design work, so I'm not too familiar with that, but generally that's the big picture. And there are many different aspects flowing into which bids might win. Of course, there's technical aspects and costs aspects, but since the funding comes from member states, the member states like to see that funding come back to their industry. So there's, of course, this aspect that plays a major role, because the idea is to have what is called geo-return, where you have the funding of the member states coming back to their industry.
Mm-hmm.
Thank you.
Thanks. Good answer. Do you have questions?
At the end of the CDF, who have the last words on the ending budgets? And these budgets, is it the budget that ESA will allow to make the project come true from beginning to end?
So yeah, in terms of budgets, we have a cost engineer involved in the study in general. So they are the ones who will make an estimate based on the design work done by the rest of the team. If during the study process we see that we will be over budget or something like that, then since the customer is also involved in the study, they can decide if they want to descope the mission, have reduced science objectives, or reduce reliability in favor of still achieving the desired budget. Or they could say, okay, I don't care about the budget, we can go over budget, and what I care the most about is to achieve the science objectives. So yeah, it's an output from the cost experts, but guided by the customer and what they want to achieve. And then this is used mostly to say whether the mission is feasible within the budget and get approval from ESA, from the member states, because they have their own ideas of what budget should be allocated to a mission like that. I'm not entirely sure how much this then feeds back into the budget that is provided for the contracts with industry. I think that also depends on the mission, how this works.
Yeah, thank you. Does anyone online have a question, perhaps? If not, then we have Mathieu here who had a question.
Yeah, hello, I'm Mathieu, so a colleague of Marnix. Here at EPFL, we focus our research a lot on space sustainability. Have you seen in the CDF that you follow, in the study that you supported, criteria about environmental impact of the space mission? Was it a KPI that was tracked along the design iterations, whether it be space debris risk or also impacts on Earth?
Yes, thanks for the question. So in terms of environmental impacts for the mission design, we do take it into account to some extent. So one of the very common requirements we have is to follow the space debris policy of ESA. So this is clearly taken into account in the mission design for orbit design, and also depending on the satellite design, it will drive what kind of disposal we can do, what kind of re-entry we can do. So in that sense, it's taken into account. I have not really seen it taken into account in terms of the design and production process of missions. So there we don't really have time and manpower to do an LCA or something like that in parallel to the design process. At least not at CDF stage. Maybe in later phases it can be done. And then another way we also work with sustainability is that we have quite a number of CDF studies that are really based on these topics of space debris, in-orbit servicing, deorbiting debris, and these types of missions. So in that sense, we also work with sustainability.
Thank you.
Mm-hmm. Thank you. Any last questions from people here or people online? If not, maybe small question, because a lot of us are, a lot of the people here are students, and they might be looking now at next steps afterwards. So you mentioned indeed the graduate trainee program and then the national trainee program. I double checked, and it's indeed the countries that you mentioned. But I was wondering, what do you recommend for students to do? What can they do now? Do you think the ESA Academy is something interesting, and when can you give a bit of a timeline of when they appear and when they should apply for these? Or and how about the graduate trainee program? When do they get published, and when should you apply, and what are the requirements?
Yeah. So for the trainee programs, the ESA ones, I think the selection process is ongoing. So unfortunately, it's too late to apply for this year. But next year there will be the next call, of course. I think it's around February, March that the positions get published, and then you can apply. And if you are successful and get selected, you will probably start in September, October. Internships, I'm not too familiar with, but I think it's more spread out around the year. And the same goes for ESA Academy activities. So there are all sorts of trainings and workshops throughout the year. So there's no specific time where it's best to look for it or to apply. Just look at what is available now, what suits your own schedule, your own agenda, and yeah, try to pick and choose from that. Yeah.
Mm-hmm. And for the trainings, for these academy ones, which one would you recommend? For example, the CDF one, what are the key takeaways from it? Is it doing a CDF or is it more than this?
Yeah. So for the concurrent engineering ones, there are a few. There's the concurrent engineering challenge where it's one team that is on site, plus we have usually 3 universities joining online, and then each team works and does a CDF study in 1 week on a specific mission that is given by ESA. So we end up with 4 different designs for the same mission, which is quite fun to see how the same set of requirements and objectives results in different designs. So that's, I think, once per year. There's the Concurrent Engineering Workshop, which is also once per year. I think there's also a CubeSat Concurrent Engineering Workshop, and there's the Alba Summer School, which is not directly organized by ESA, but there's a follow-up event that's usually hosted also at the Concurrent Design Facility in Belgium by ESA Academy. And yeah, all of these, the goal is to do a CDF study in 1 week with a team of 25 to 30 students. So that's quite intense, but also quite fun. For the other ones, I haven't taken part in any of them, so I'm not too familiar, but yeah, there are many other options as well.
On a personal note, I can recommend the Clean Space course, which I did, which was quite good. Okay, last question.
Sorry, I saw on the ESA webpage that the opportunities for the internships are in November. Is it possible to then apply like this, like sending some mails all the year, or it is always during November that we can?
Yeah, generally if they publish everything in November, then that's the time where most of them will be available, and you have to apply for a position that is being offered that is open. There might be other ones sporadically throughout the year, I'm not entirely sure. But your highest chances of finding something is then if the website says November, it's November. Yeah, I'm not sure you will have much luck with spontaneous applications, but yeah, you can always try.
Okay, thanks. I think it was very interesting and also good for the students to see what they can do afterwards, and how, for the ones that participated in the CDF class, how it's actually applied in real life. And because the way you said, having 4-hour sessions, 1 or 2 times a week or something, quite similar to what we did essentially.
It's crazy, yeah.
So the similarities are quite interesting. But thanks a lot, Justin, and thanks a lot for everyone who joined online. I think we can close the call now. So a big round of applause for Philip.
Yeah, thanks everyone. Thanks for having me on this webinar.
Yes, thank you, and speak to you soon.
Bye-bye.
Yeah.
Thanks.
Bye.